Hello and welcome to SudoKanard. Here is a Sudoku, a very special Sudoku that I set a few days ago and which has stumped a few of my Sudoku friends because the underlying arithmetics is, well, seems to be very tedious, but I try to show that it can be somewhat elegant and not that tedious. So, what is the rule of this special Sudoku? Every time you have a number that overlaps a 2 by 2 array, like this is the absolute value of the determinant. So, what does this mean? It means that whenever you have 4 digits here, you compute both diagonal products and then you subtract the smaller product from the bigger product. Let's take an example. Let's say we have a 2, a 5, a 7, and an 8. Then on this diagonal, you have a product of 16. On this diagonal, you have a product of 35. Then you make the bigger minus the smaller, that makes 19. And in this case, this box would contain 19. And that is the special rule of this puzzle. Now, how do you tackle such a problem? Well, you need to understand a few things about how we obtain such a result as 0 or 1. 0 means that both products are the same, and this is a cross-product criterion, which means that those columns, those rows are proportional. And we don't have 1, so what remains? All digits between 2 and 9, obviously, but 4, 5 and 7 must be included because there are no multiples of 5 or 7 between 2 and 9. So the digits that remain are those, and there are some proportionalities between them. For example, you can have 2 and 3, and they're doubles, 4 and 6. This makes a determinant of 0. And you can do any permutations of them. I mean, you can put them in almost any order as long as you have 2 multiplied by 6 on some diagonal and 4 multiplied by 3 on the other diagonal. Another option is to have 6 and 9 on the second row or on the first row. Likewise, you can permute both. You can switch the rows, you can switch columns, and you still have a product of 18 on both diagonals. Another option would seem to be 4 and 6 and 6 and 9, but that would repeat the 6 inside this box, so this is not available. Another option is to have an 8 somewhere. This is 3, 4, and 6, 8. Multiplying by 2, you get this, and that's a product of 24 on the diagonals. So you can convince yourself that these are the only options for those 4 digits, which are 3 options here, you're telling me. That seems to be a lot of work to do now. But now let's ponder this determinant of 1, which means that this product and this product are consecutive numbers. And some interesting thing about it is that when 2 numbers are separated by 1, they can't have any common factor. If those digits have a common factor, then those 2 products have this common factor, and their difference has this common factor as well, and it couldn't be 1. So these two products have no common factor, and those two digits must have no common factor, meaning that we must take among all those dominoes 2, 3, 2, 4, 2, 6, etc., which are the ones with two digits that have no common factor. And if you look closely, you see that only the smaller ones have no common factor, because in every instance the bigger ones have a common factor because there are some kind of multiples of the other ones. Here we have a common factor of 3, here it is 4, here it's 2, 3, 2, 3, 2, 3, 2. So the only options for this domino are 2, 3 and 3, 4. So these are 2, 3 or 4. And you can see that 6 must be on this top row, together with 4, 9 or 8. So that's a start, and 3 has to be among them. Now there is some elimination to do. So what happens if we make this a 3? What are the options? Well, let's have a look at this. We know that the difference between both diagonals is 2. So both products have the same parity. Now, can it be an odd number? If this is an odd number, then all these 4 digits must be odd, and those 2 digits will be even, meaning that the determinant will be an even number, which is not the case. So it's not possible for all 4 digits to be odd. There must be at least one even number. But actually, both products must be even numbers. So there has to be at least 2 even digits here. And where is the trouble? Well, if we have 2 even digits here, then we can't have 3 even digits here. So we can't have this, we can't have that, so we must have this, meaning that this is 9, this is 6, this is 2. And now the remaining even digits here must be 4 and 8. Let's imagine they are like this. Then there's a new issue, which is that both diagonals are multiples of 4, and their difference therefore must be a multiple of 4, but 2 is not a multiple of 4, so this breaks. And well, that's a little convoluted, I grant you that, but this proves that 3 can't go in this cell. So let's remove 3 from here, and 3 has to go there, making this a 6 or a 9. This is a 2 or a 4. And now this one must be 6, 4 or 8. And we know that we have an even product on this diagonal, and we must have another even product on this diagonal. Where should we look? Well, because I know the story, I know that 2 here will be problematic. And why is this the case? why is 2 a problem here? Well, let's have a look. If 2 is here, then on top of the 2, we can't have 8. So 8 must be somewhere around here. And what was the logic again? I don't quite remember. So we have here an even product, and we must have another even product. So let's recall that 6 is here. So here we must have 4 or 8. So this product is a multiple of 4, and this one is not a multiple of 4. So this must be an odd digit, meaning 5, 7, or 9. Oh, there was something much more elegant, but I don't remember what it was. So what do we have here? And what do we have here? Here it must also be an odd number, because those two digits must have no common factor. So this one must be 4 or 8. And this one must be an odd number, meaning 5, 7, or 9. That's correct. Now, what happens here? What happens is that 3 multiplied by 9 would make 27. No digit would be big enough here. 3 multiplied by 7 would be 21. No digits would be high enough here. So this has to be a 5. This is 15, meaning that this has to be 16 or 14. So this is 7 or 8. I'm absolutely certain that there was a much more elegant argument, but I don't quite remember. So now what do we have here? This is at least 20, this is at most 18, so the only way is to have this and this. So this is 15. Both of those are suitable, but only 7 goes here. And this is now, this is now an 8, which doesn't work at all for this. It doesn't work, just doesn't work. So that doesn't work. Oh, there was something much more elegant. I'm really sorry that I couldn't find it. So this is a 4, and now the only possibility is to have 6 and 8 in here. Okay, so we still need to have 2 somewhere. It won't be there because this would break, so 2 must go here. And it wouldn't be here because if 2 were here, those would be odd and the determinant would be odd. Now we are left with placing 5, 7, and 9 in those cells. And what do we have? Well, that's the same story as previously, meaning that this is a minimum of 20, this is a maximum of 18, and this extreme case produces 2 as a difference. The other cases make more than 2 for a difference. So we must have those. That's a 7, and you can check that 28 minus 27 is actually 1. So there's only one option for this box. Now, where do we look? Well, I suggest we have a look at this. Let's have a look at how we make this determinant equal to 2. 9 times something is a lot, but there are, well, not that many choices. With 3, that's 27, 5 would work. So let's recall that 3 and 5 would work. Let's try 4. That's 36. Well, we won't have 36 plus or minus 2 wouldn't be divisible by 5. 5 is not available. 6 would make this 54. That's too much. We won't reach anything by multiplying by 5. So that's the only option. This diagonal makes 35, so this is 34 or 36. Only 36 works. Now, what are the remaining digits? Well, 1 and 2 are not here, so 1 and 2 must be there. We must have 1 and 2 in this determinant of 4. The other digits are 6, 7, 8, and 9. So what will we have to complete this? Well, 1 and 2 says, well, let's say 2 is here. And 1 is there. So that's a product of 2. Those must have a product of 6. That's impossible with those digits. So 1 and 2 must be neighbors. And those products must have a difference of 4 with those digits, with those big digits. If we put a 9 here, that's 18. We won't get any close to 14. 8, that's 16, same story. 7, that's 14. We won't go anywhere near 10, so it has to be a 6. Making this 12, and the only option here is 8. Well, of course, they need not be placed in this order, but those are the only 4 digits that work for this determinant of 4. These are 7 and 9, and those digits shall be placed in due course. But let's just note that 8 is not in this column, and 6 is not in this one. So this is a valid option, but there are not that many options. 6 must be here, 8 must be there, and what I just deleted is that we must have 6 plus 2 on one diagonal and 1 times 8 on the other diagonal. So actually, this is a 1-6 pair, this is an 8-2 pair. And we have to disambiguate that using the rest of the grid, obviously. Let's have a look at this. Here we must have 4, 6, and 8. But we know that we have a determinant of 2. So it's not possible for those digits to be 4 and 8, or the determinant would be a multiple of 4. So this can't be a 6, and we must have a 6 in one of those cells. Those digits now must be 2, 3, and 7. Well, this one can't be 7 actually because of the given digits in the grid. Let's have a look. How can we have a difference of 2? Well, 7 makes a minimum of 28, and this is a maximum of 24. The difference is 4, so 7 wouldn't work here. 7 is here. So we now know we have 2 and 3, and we have a 6 somewhere. So what do we have? 6 multiplied by 2 or 6 multiplied by 3, with a 4 or an 8 here. But 6 times 2, that's 12, that's a multiple of 4, and if we put 4 or 8 here, we have a multiple of 4 for the determinant. So this won't work. 6 is opposite 3 on the diagonal. That's 18. We have 2. 4 wouldn't work, 8 will work. So 4 is up there. And we have a 6-8 pair here. And those are 1, 5, and 9. And we must remember that 6 is opposite 3 and 8 is opposite 2 on the diagonals. So that's it for the time being on those cells. Well, something can be done about this actually, now that I think of it. Let's have a closer look at what can be done, perhaps. Let's have a look at this. This diagonal has a multiple of 4. This one must be even, but not a multiple of 4. So this must be 2 or 6. But 42 is too big. We can't reach 40 here. So this must be a 2. That's 14. So this must be 12 or 16. And this digit is a 3 or a 4. Let's have a look at this. We now have 2 multiples of 3, and this one is even, so this one must be odd. So this is an odd digit, it's not 1, so it has to be, well, 3, 5, 7, or 9, but not that many of them will work. 3 can work with a 1. That's 9 minus 6. It would work with a 2, but it's not available. 3 times 5, that's 15. This would have to be a 2 or a 3. They are not available. So 5 is ruled out. 7, that's 21. We would need 18 or 24, meaning that this would have to be 3 or 4. They are not available. 7 is out. What about 9? That's 27. This would have to be 24 or 30, and 30 would work with a 5. So there are still 2 options here. 3 and 1, 9 and 5. And that's all for the time being for this part of the grid. Now we must move on to box 9. There again, it seems to be very tedious, but there are not that many options if you consider the fact that all 3 determinants are odd, meaning that one of the diagonals must have an odd product and the other one must have an even product, meaning that one of the diagonals must have 2 odd digits. And this is true for all 3 squares, all 3 2 by 2 squares here. Let's say those are odd. Then what happens here? We still need 2 other odd digits, and we must have one on one of these diagonals and one here. I wouldn't put 2 odds here, because then those would be even and this determinant couldn't be 1. So we must have this as an odd diagonal and this. So if this diagonal is odd, then we have this checkered pattern with odds and evens. Now let's imagine that the odd digits are here. Then we need two other odd digits here. They can be either here or there, but if they are here, that puts two even digits here and one is not feasible. So in this case, this diagonal must be odd, meaning that there again we have a checkered pattern for these 8 cells between odd and even. Well, that's not quite sufficient to solve this part. But now let's ponder the fact that all those diagonals are a product of 2 odds or 2 evens. The remaining odds are 1, 3, 5, and 9. The remaining evens are 2, 4, 6, and 8. Now let's have a look at the available products. The available odd products are 3, 5, 9, 15, 27, and 45. The available products with even digits are 8, 12, 16, 24, 32, and 48. And now we must group them with those in the cases where they have a difference of 1 or 3. And you can see that most of them work actually, but 3 does not work. 3 does not work. It doesn't have a difference of 1 or 3 with any of those. 3 works with 8, 9 works with 8 and with 12, 15 works with 12 and with 16, 27 works with 24, 45 works with 48, but 32 doesn't work with anyone. So it leaves a lot to work with. But let's have a look at this cell. This cell is either an odd or an even digit, obviously, but it has the same parity as those 3 cells, meaning that we will have to use this with all available products of them. But we've ruled out 1 times 3. So this digit can't be a 1 or a 3. And we've ruled out 4 times 8. So this digit can't be a 4 or an 8. Now only 4 digits remain. And those are 2 and 6 for the even digits, and 5 and 9 for the odd digits. So we only have 4 candidates for this digit. Let's have a look. What if I make this a 2? Well, if I make this a 2, then I need to place 4, 6, and 8 somewhere in those cells. And something else I should mention is that the possibilities for this determinant of 1 are not that many actually. Before making this a 2, let's list what the options are for determinant of 1. The differences of 1 are not that many. There are 9 minus 8, 16 minus 15. So the only options for determinant 1 are 9 minus 8, which would be 9, 8, 2, and 4 in some order, and 16 minus 15, which is 8 times 2 minus 3 times 5. So we now know that 6 can't appear in this square. So we can rule 6 out from the list. we only have 3 candidates for this digit. That's it. And actually 2 is the less constrained of those, it seems. But let's make this a 2 anyway. We know that this is 4 or 8, so 6 has to be in one of those cells. Let's say 6 is here. Now, what happens here? We have 12, and now we must have 15 here, or 9. So it has to be either 1 or 9 here, or 3 and 5 here. But if we make this 1 and 9, we can't put 1 and 9 here. So we have to put 3 and 5 here, but then we can't put 3 and 5 here. So whatever we put here, we can't put here, and no choice is available here. So 2 and 6 here won't work, and 2 and 6 here won't work for the same reason. So 2 can't be in this center. 2 is not a valid candidate for this. So both remaining digits are 5 and 9. And one of them will be excluded as well. And I don't remember which one it is, so let's try 5. If I make this a 5, then this is a 3. And we have 2 and 8 in some order, and we have 1 and 9 in some order here and there. Let's say 1 and 9 this way. So this is 5, and now this must be 8 with 2 and 4, and this must be 8 with 2 and 4, so this must be 2, 4, 8, and 6, and this works, so 5 seems to be a valid candidate. Let's try with 9, and let's see why it won't work. So we have 1 here, 2 and 4 there, 5 and 3 there, and this 5 and 9 say that those are 6 and 8, but it's not possible because those are 2 and 4. So 9 won't work either. So we now know that the central digit is a 5 together with a 3, and there are 2 options, which are 1 here, 9 there, or the opposite. In which case, if this is a 9, then we have 6 and 8, and because of this, this is 8 here, 6 there, and the other option is 8 here, 6 there, on the right-hand scenario, and now we must place 2 and 4, and 2 is here, 4 is there. So in the left-hand scenario, that's 8 minus 5, and this is 48 minus 45. Now, how are we going to resolve? How are we going to find which is the right one? Well, that's with this, with those determinants of 2. How can we have a determinant of 2 with 2 and 1 with 8 and 9? Let's have a look at 8 and 9. How do we make those? Well, how do we really make those? Let's have a look at those multiples of 9. Which are the multiples of 9? Well, this one is even, so this one has to be even as well. So we must put an even digit here, and 8 and 4 are not available. So this can only be 2 or 6. First case, 9 times 2, that's 18. So we need 16 or 20. And 16 would need another 2. So it won't work. 9 times 6, that's 54. We need 52 or 56. Only 56 would work with a 7 here, but 7 is not available. So we now know that this right-hand option is not possible. And this 8 and 6 disambiguate this. This is 6 and 8 together with 2 and 3 here to fulfill this 2 determinant. So that's not a 9, that's not a 5, that's not a 1. Now, how will we continue? How will we go on? Let's have a look at those digits. They must be 5, 9, 7, 8. How can we do that? 9 wouldn't work here because this determinant would be a multiple of 3. So this has, oh sorry, this, I said 7, but that's 6 actually. And 6 wouldn't work either for the same reason. So this is either 5 or 8. Now, what is that really the right place to look? Not sure about this. Maybe I should look at this instead. Yes, that's an even number, so that must be an even product. 2 and 6 are not available. This is 4 or 8. But now here, 3 multiplied by 8 makes 24. No digit here will be big enough. So that must be a 4. That's 12. So this must be 10 or 14. So this is 5 or 7. And now you see that 35 and 56 are much too big for this product to work. So this can't be a 7. And 40 won't work either. So this can't be an 8. So that's 25, and this must be 24 or 26. Only 24 works with an 8. And this disambiguates that. 2, 8 here, 6 and 1 there. We need now 3, 6, 7, and 9. Here only 3 works. That's 4. This will be 6. Okay. And now we have 6, 7, and 9 in those cells. And we must have a difference of 3 here. That's a multiple of 8. And that must be an odd digit. So it can't be 6. This is 6. What about those? 35 would work with 32, but it would require a 4 that is not available. So this is actually a 9, making this a 7, this a 9. That's 45, and this will be 48, making this a 6. And now we get an 8 here, a 9 here, 1 and 5. And the end should be much easier. We need here 1, 2, and 4. And here 3, 7, and 9. Oh, that's not resolved yet. Let's have a look anyway. And let's have a look at this. How do we make this a 4? Well, this product is a multiple of 4, so this one must be as well, so this can only be a 4. That's 36. This must be 32, but 4 is not available, so it must be 40. This is a 5. Now 3 goes there by Sudoku, making this a 4, this a 9, and this a 5, this a 7, this a 3, and this a 9. That's a 1, that's a 4, that's a 2. And those are 1 and 7. Here we have 1, 2, and 7, so that's a 2. And a 1, 7 pair. Here 6, 8, 9, so that's a 6. 8 or 9 here. And we've stored the possibilities. 6 and 8, 6 and 9 both work here. 6, 9. Well, let's not be too fast because those assumed all 4 digits to be different. And now we could have a 6 here with 9 times 4, but 4 is not available. So no repetition here. But what are the digits available? 1, 7, well, 7 or 1 wouldn't work here. And the other ones are 2 and 4. So, 4 is not available either, so that's a 2. And the only possibility is to have 3 here and 9 there. Now we need 1, 6, and 8. 8 can only go here, 6 here and 1 there, making this a 7 and this a 1. Now we need here 2 and 7, and this is a 6, and this is a 3. And the final digits now are 5 here, 4, 7, making this a 1, this a 7, that's a 1, that's an 8, and that's a 9. And this finishes this solve of, well, this quite tedious absolute determinant that I had the notion to create a few days ago. Well, that was more a proof of concept than a real puzzle, actually. But I found some of it to be really fun. Well, that's probably some deviance of mine. Well, thanks for watching this very long video, and see you soon on SudoKanard.